students, today we will learn that what is Reynolds Transport Theorem. Reynolds Transport Theorem is in connection with fluid flow, means in connection with fluid dynamics, and it is based upon the conservation principles of fluid dynamics. So at the end of this lecture we will be able to understand that what is Reynolds Transport Theorem. We will derive the necessary equations, as well as you will be able to learn that what is the physical significance of Reynolds Transport Theorem. So before understanding the complete derivation, all those equations, we have to learn a few things in connection with Reynolds Transport Theorem. First thing is control system. Okay, what is control system? The collection of mass particles is control system. For example, suppose there is a bucket which is full of water. Okay, since water contains H2O molecules, means water content is composed of mass particles, so the water content inside the bucket can be considered as a control system. Similarly, in case we take a handful of sand in our hand, then those sand particles are mass particles, so those sand particles can also be considered as a control system. So in simple way, the collection of mass particles, the entire collection, can be considered as a control system. Now what is control volume? The region or space for analysis, and over here we are talking about the Reynolds Transport Theorem. So in connection with Reynolds Transport Theorem, the region or space which is kept for analysis, we can say through which the fluid is flowing up, means going inside that region and coming out like this. So the region or space kept for analysis is what the control volume is. For example, in the same case of the bucket full of water, the volume of bucket inside which the water is kept, that volume is what the control volume is. Remember that control volume is a geometric attribute. Okay, and control system is actually a mass attribute, means collection of mass particles is what control system is, and control volume is a region or space for analysis in regards of this Reynolds Transport Theorem. Now how many types of control volume can be possible? That is what we are going to learn in this slide. Okay, one type is fixed control volume. Fixed control volume is what? In case the control volume doesn't changes its position, it remains fixed over its position, then such type of control volume is called as fixed control volume. For example, this is a case of nozzle through which some fluid is flowing, say water is flowing. Then in case we are considering the control volume, that is the volume of this nozzle, then this can be considered as a case of fixed control volume, because control volume remains intact over its position. The water goes inside the control volume and ultimately leaves the control. Now one case is moving control volume. Suppose this is an helicopter and we are interested to find out that how air goes and interacts with the rotor of the helicopter and leaves the rotor. So we are assuming a control volume around the rotor. You can see this red colored outline is showing the control volume, which is keeping the rotor inside it. Okay, air is going inside this control volume, ultimately leaving it. Okay, so since helicopter moves in air with some speed, so we have to move this control volume with the speed of helicopter. So this is an example of a moving control volume. Okay, this control volume inside which rotor is kept and helicopter is moving can be considered as a moving control volume. And one type of control volume is deforming control volume, means the shape of control volume is changing. For example, this is the balloon which is inflating, air is going inside the balloon, so continuously the volume of this balloon is changing. In case we are considering the membrane, the elastic membrane of the balloon as control volume, then with inflation of balloon, that volume of balloon is increasing, so the control volume size is also increasing. This is the case of deforming control volume. Next is, we will take letter B as a general symbol of fluid property. Which type of fluid property? Those properties which are having their significance in Reynolds Transport Theorem and which are having their significance with fluid flow. Okay, for example, momentum of fluid. When fluid moves, it has some momentum, so momentum has its significance with fluid flow. Similarly, angular momentum, in case there is some whirl component, rotating component in fluid, then angular momentum is also a fluid property in connection with fluid flow. Similarly, total energy. Okay, because with movement of fluid it can have kinetic energy, it can have pressure energy. So total energy E is also a property of fluid. Similarly, total volume and total mass, like this. So the fluid properties which are in connection with fluid flow are not limited to only these many properties, but these are some prominent properties of fluid flow which are having their significance in Reynolds transport theorem. So for all these properties we will take B as a general symbol. So B means set of all these properties which are having their significance, their importance in fluid flow. Second thing is, we will take beta as the specific property of fluid. Specific property means in case we are dividing the property, whatever that property is, we are dividing the property B with the mass of the system, then we will get the specific property, that is beta. For example, in case we divide the angular momentum of the fluid with the mass of the fluid system, then it is specific angular momentum. Similarly, in case we divide the total volume of fluid with the mass of fluid, we will get a specific volume. In case we divide the total energy of fluid with the mass of fluid, then we will get specific energy, like this. Okay, so beta is the general symbol for a specific property of fluid we will take, and B is a general symbol for all the properties of fluids which are having their significance with fluid flow and Reynolds transport theorem. Okay, now we are going to derive the Reynolds transport theorem RTT for a fixed control volume. We know what is fixed control volume, which doesn't changes its position with respect to time. Now I am taking a case, suppose there is a river in which water is flowing, an open channel in which water is flowing, and I am considering a fixed control volume CV. Okay, this black colored outline is showing the control volume, fixed control volume inside this moving water system. Okay, now what happens, that in case we are fixing this control volume, then water is entering inside this control volume and ultimately leaving it. It is like this. Now suppose we are starting our analysis at time t, and this is the control system. This red colored outline is the control system inside this control volume at time t. Okay, we know this control system is the collection of mass particles. So whatever water content is there inside this control volume, the entire mass of that water, suppose we are taking as control system, and this red outline is just differentiating the control system from the control volume. Okay, so exactly at time t we can see that control system is exactly fitting inside the control volume. Okay, so we can say that whatever property of control system is there at time t is exactly equal to the property of control volume at the same time t. BCST is equals to BCVT. This is how we can write this thing, because at time t we are starting our analysis, and at that time, since control system is exactly fitting inside the control volume, so whatever property the control system is containing is what the property of this entire control volume, because control system is exactly fitting inside the control volume. So both are equal, we can say like this at time t. Now suppose at time t plus del t, the control system which was previously just fitting inside this control volume moves out of the control volume. Okay, we can see that new position of control system is AFCB, this region. By red colored outline I am showing the control system, the current position of control system after time t plus del t. Okay, now after time t plus del t, we can see that this control volume and control system consist of three regions. The region first, which means the amount of control system AFCD, which is still inside the control volume. The region second, which is the amount of control system which has moved out of this control volume. And region third, the new fresh control system which has entered inside this control volume, that is equals to AECF. So AECF is the new fresh amount of control system entered inside the control volume, and ABCD is the amount of control system which has left the control volume, and AFCD is the amount of control system which is still inside the control volume. It is like this. Now at time t plus del t, the control system's property B can be written as BCS t plus del t equals to the property of this region first plus property of this region second. Property of region first at time t plus del t plus property of region second at time t plus del t. Region is that now the control system which was previously just fitting inside the control volume, it is A F, C and B. So it is composed of these two regions. So at time t plus del t, control system's property would be B second t plus del t plus B first t plus del t. Now in this equation, to the right hand side, I am adding B third t plus del t as well as subtracting the same minus B third t plus del t. So I am adding some entity to the RHS of this equation as well as subtracting. So there is no change in this equation, the context remains the same. Okay, now what is B third t plus del t? The amount of control system, the amount of property of control system which has entered inside this control volume at time t plus del t, that is what B third t plus del t. Okay, so hope you would have understood this thing, that I am adding the B third t plus del t as well as subtracting, so there is no change. Now you can see easily over here that the region first and region third, okay, is actually the control volume after time t plus del t, because now the control volume is what? AECD. Okay, that is composed of region first and region third. So this B first t plus del t plus B third t plus del t can be written as BCV at time t plus del t, and other two terms, those are B second t plus del t and minus B third t plus del t, remains the same. Okay, now this is our equation second. What we have done, since B first and B third is equal to the property of control system at time t plus del t, so we can write BCV t plus del t for this thing, B first plus B third, and B second t plus del t minus B third t plus del t remains the same. Okay, this is our equation second. Now in case I subtract the equation 1 from equation second, what I will get? BCS t plus del t minus BCS t over the LHS, and over the RHS BCV t plus del t minus BCV t plus B second t plus del t minus B third t plus del t remains the same. Okay, so this is our new equation we have arrived. Now in case I divide both the sides of this equation by del t, then the equation looks like this. Both the sides I am dividing with the amount of time elapsed in this process, that is del t. So like this I have divided. Okay, now in case del t tends to 0 for these two terms, this BCS t plus del t minus BCS t upon del t can be written in differential form, that is dB by dt of the control system. Similarly, BCV t plus del t minus BCV t upon del t can be written as dB upon dt for control volume. Okay, it is written in differential form, and B second t plus del t upon del t minus B third t plus del t upon del t remains the same. Okay, and this is also a part of control system because the mass entering inside and mass going outside, so these are also the control systems, because what is control system? Control system is the collection of mass particles, that's it. So we can write the subscript CS also over here. Now what is this B second? B second is the amount of property which is leaving this control volume at time t plus del t. Okay, now in case the mass of the control system which is leaving this control volume, which is associated with this region second, is M out, then this B second can be written as M out into beta out, because what is beta? Beta is the specific property. So beta means what? Property per unit mass. So this B second can be written as amount of mass which has gone out of the control volume into the specific property associated with that region, beta out, the region A, B, C, D. Same thing for this B third, I can write the amount of mass which enters inside the control volume in time del t. This is the mass in into the beta associated, the specific property associated with that entrance of mass upon del t. Okay, now this M out is what? The M out is the amount of mass, amount of control system which is leaving this control volume, that is equals to the mass of portion A, B, C and D. So this M out can also be written as the mass flow rate when the control system is going out of control volume, the mass flow rate over there when it is leaving, into the amount of time for which it is moving out. See, this entire process is happening for del t amount of times. So the amount of mass flow rate over the exit, that is over the portion ADC, the mass flow rate over there, into the amount of time elapsed, can be written as the M out. Okay, so in place of M out we can write M dot out into the del t. M dot corresponds to the mass flow rate at exit, and del t corresponds to the amount of time for which the control system is exiting out of the control volume. Okay, same thing, this M in is what? The amount of mass which is transferring inside the control volume. Suppose over there, when it is taking the entry, over there the mass flow rate is m dot in. So m dot in into the time elapsed is the total amount of mass which is going inside this control volume. So m in can also be written as m dot into del t. Okay, now you can easily see that we can cancel out this del t. Okay, so in case we cancel out this del t, our equation ultimately becomes this dv by dt cs equals to dv by dt cv plus m dot out beta out minus m dot in beta in cs. Okay, now in case m dot in beta in is taken as positive and m dot out beta out is taken as negative, the amount of property which is entering inside the control volume is taken as positive and amount of property which is leaving the control volume is taken as negative. So in that case our equation becomes like this: dv by dt cs equals to dv by dt cv plus m dot in beta in minus m dot out beta out. Okay, now this expression m dot in beta in minus m dot out beta out is what? The net amount of property which is accumulating inside the control volume per unit time. This is the amount of property which is going inside the control volume per unit time. This is the amount of property which is leaving the control volume per unit time. So what is the difference? Difference is the net amount of accumulated property inside the control volume per unit time. So for this big expression m dot in beta in minus m dot out beta out, we can also write this general expression m dot beta cs. Okay, this is what our Reynolds transport theorem is. Okay, which says that the physical significance is like this, that dB by dt control system says that amount of change in property of control system per unit time is equals to the amount of generation of property inside the control volume per unit time plus amount of property accumulation inside the control volume per unit time. Once again, the amount of change of property per unit time of control system is equals to the amount of generation of property inside the control volume per unit time plus amount of property which is accumulating inside the control volume due to mass inflow and outflow. This could be understood by this simple example. Suppose that this is a village, a region. Okay, this is a village, and in the village per year 1000 tons of food grains are entering, and in the same year 800 tons of food grains are going out. Okay, it is like this: 1000 tons of food grains are entering inside and 800 tons of food grains are going out per year. Okay, now net amount of accumulation of food grains inside this village per year would be 1000 minus 800 because 200 is remaining inside. Now suppose the villagers, the farmers of the village can cultivate 100 tons of food grains per year. Okay, now net rate of development of food grains per year inside this village would be net amount due to accumulation of in and out, that is 1000 minus 800, so that is equals to 200 tons of food grains are accumulating inside and 100 tons are cultivated per year. This is the amount of generated food grains generated. So 100 plus 1000 minus 800, that is equals to 300 tons per year would be the net revenue, net development of food grains per year inside the village. So same, the analogy is same as like that of Reynolds transport theorem. The rate of change of property of control system per unit time is equals to the rate of generation of property inside the control volume per unit time plus rate of accumulation of property inside the control volume per unit time due to mass inflow and outflow. Now this m dot beta cs is what the net rate of property accumulation inside the control volume per unit time. Okay, this can also be written as the integration of elemental accumulation of property inside the control volume per unit time. This dm into beta is the small elemental rate of property accumulation inside the control volume, but dm is the elemental mass flow rate over here. So this dm, elemental mass flow rate, can also be written as the volume flow rate into the density. Now what is volume flow rate? Volume flow rate, we know this thing, it is equals to the velocity of fluid into area. The velocity of fluid in which direction? The velocity of fluid normal to the area. So Vn corresponds to the velocity of fluid and dA corresponds to the area through which the fluid is exiting with velocity Vn. Here Vn is the velocity normal to the area through which fluid is coming out. So Vn into dA is the elemental volume flow rate, into the density is what? The elemental mass flow rate. So in place of dm I can write rho Vn into dA and beta remains the same. So integration cs beta rho Vn into dA, this m dot b, this is the net amount of property accumulation, can also be written as in this form, that is integration Cs beta rho Vn into dA. So ultimately our Reynolds transport theorem can also be written as dB by dt Cs equals to dB by dt Cv plus integration Cs beta rho Vn into dA. Now one more thing over here, that this m dot beta is the net amount of property accumulation inside the control volume. So it could be positive and it could be negative also. It will be positive in case the net amount of property entering inside the control volume is more than the net amount of property which is going out of the control volume. Okay, and in case net amount of property is going inside the control volume is lesser than the amount of property which is leaving, in that case m dot beta Cs would be negative. So hope you would have understood the Reynolds transport theorem and its physical significance. Thank you.